Now last week we covered how to get to the actual definition of a derivative by using our knowledge of slope and limits. Now this week, instead of going into the shortcuts for derivatives as I had originally planned, I'll save that for later. This week I kind of want to clarify and reinforce our understanding of derivatives by actually using it to find the equation of the tangent line. Now, recall that a tangent line is a straight line that intersects our function at exactly one point. Therefore, it can be denoted in slope-intercept form as y equals mx plus b, where m represents the slope of the tangent line and b represents the y-intercept of it. Now, recall that derivatives is merely giving us the slope of the tangent line. Therefore, when we're plugging a value x into the derivative, we're finding the slope of the tangent line at that point. Therefore, in terms of the equation of the tangent line, the derivative technically represents m. So if I had a function over here, f of x equals 3x cubed plus 4, the derivative of that, which I've already done, is f prime x equals 9x squared. Whatever value I plug into x for f prime will give me the slope at that value x, but it is not the equation of the tangent line itself. So knowing the slope m from f prime x, I still need to find out my y-intercept. So over here I've kind of summarized the rules we'll be using, well, not really rules, but kind of directions that kind of summarize how to get to this slope-intercept form. So to start off, these are both equations of straight lines, but just in different forms. We're going to use the point slope form because it's shorter and it just goes directly to it. And we're going to plug in some values that'll eventually get us to this slope-intercept form. So the first step, as I said earlier, we're going to use f prime x to find the slope of the tangent line, which is m. Second, because our tangent line intersects the original function at exactly one point, we can plug in that x coordinate into our original function to find the y coordinate. Now that new coordinate x1, y1 is shared by both the original function and the tangent line. Therefore, we can plug it into our point slope form as a valid point, and then just simplify it as for step 3 and get to y equals mx plus b. So let's do an example. If I had f of x equals 4x cubed plus 1, and I wanted to know the tangent line equation at x equals 2, well, first let me take the derivative of this, which I've already done, is 12x squared. Now, first step, we need to know the slope here. So we're going to use f prime function, plug in 2 to find the slope. So 12 times 2 squared, 2 squared is 4, times 12 is 48. Therefore, 48 is the slope of our straight line or tangent line. Second, we need to now find a coordinate x1, y1 that we could plug in here to later simplify. So we're going to use our original function for that, because remember, if we can't plug it into the derivative, because the derivative relates m to x, whereas the original function relates y to x, and that's a common misconception that people have. So if I used the original function, f of 2 is equal to 4 times 2 cubed plus 1, and that equals, well, 2 cubed is 8, times 4 is 32, plus 1 is 33, and this is our value for y1. So our actual coordinate would be 2, because that's what we're given, and 33. And this is our y1, x1, y1 coordinate. Now we have the two necessities. We're going to plug into point slope form and get our final answer in slope intercept form. So y minus y1, which is 33 based off our coordinate, equals the slope, which is 48, times x minus x1, which is 2, and we were given that. So y minus 33, if I distribute the 48, I get 48x minus 96, and we can already kind of see it kind of turning into that slope intercept form. We're going to add 33 to both sides and get 48x minus 63, and this is the equation of our tangent line. Meaning, if I graphed this and I graphed our original function on top over here, I would see that at the value on our horizontal axis, x equals 2, it'll intersect at only one point. And that's pretty much it. Now, as an extension of this lesson, say I wanted to find out the equation of the line that is what is called normal to our tangent. So when you say normal in math, it basically means perpendicular 90 degrees. Well, it's the same thing as before. We're gonna use f prime x to find our derivative. However, f prime x will give us the slope m of the tangent line. If you want the line perpendicular or normal to that tangent line, we know that the slope of anything that's perpendicular to a straight line would be the inverse of that slope, and we change the sign. So if our slope was m, the slope of the perpendicular line would be -1 over m, and whatever number we get there, we just go through the motion, and that's pretty much it. And that would give us instead the line that is perpendicular to that exact point on our original function. And that's pretty much it for this video. Hope it was useful, and I hope it wasn't too confusing or too rambling. And yeah, I'll see you guys next week. Peace.